Hello and welcome back. This is Dr. Churchill, and we are ready now for our module on the planet Mars. And I think you will find Mars is quite a fascinating planet. It had a very interesting history, including one in which it was partially covered with an ocean and had a thick atmosphere and also a magnetic field, a global magnetic field. And I have a few videos that will go along with this lecture that will talk about that in some detail, not a whole great deal, but it's very interesting. So the planet seems to have had a transformation when it was still quite young. And I just want you to understand that when you watch the videos, especially the one that talks about the past, that they'll be talking about the properties of Mars in the past, and I don't want you to get those mixed up with the properties that it has today. It had a very short period of time where I think it was about 200 million years, where it had this atmosphere, it had the oceans, and it had the magnetic field. And then something happened, and there's several theories as to what might have happened. And one of the videos is a theory where it was hit by a large impactor that may have caused some problems. Anyhow, we're going to go through Mars, take a little tour of how it compares to Earth and what it looks like today, and a little bit of discussion of its past, but a lot of that will be in the videos as well. So we'll move on to the next slide. Our learning objectives today are going to be first just one little slide that's for fun about the history of the culture behind Mars. There's a fascinating history about Mars, but I'm just going to tell you about one little piece of it that's kind of fun. But then we're going to look at Mars today. We're going to look at its features. We're going to look at its relative properties compared to the Earth, and we will examine its major geological features. And we'll show some evidence that liquid water has flowed on Mars, certainly in the past, and perhaps even today. So we'll talk a little bit about what may have caused Mars to go through this major transformation and talk about its present-day habitability. We're also going to be talking about the seasons on Mars, which are much more extreme than those on Earth. And so there'll be a little tutorial on seasons as they behave on the Earth, and then we'll talk about Mars. And one of the things that will be important here is that Mars's seasons are more extreme mostly because it has a more elliptical orbit around the sun than the Earth does. So we'll be talking about that and how that elliptical orbit causes the seasons to be more extreme than they are on Earth. So we'll briefly chat about evidence for life on Mars. I usually have a very long set of slides on that I've cut out. I might mention something about those, but I don't have the major slides on one of the old missions. And then, okay, there's a video at the very end that is an optional on the video sets, and one of them is about what would it take to send people to Mars. It's about a 10-minute video. It's a very fast-paced, sort of blah, blah, blah this and blah, blah, blah that kind of video. It's really very, very good information content if you're interested in, especially about the medical problems in sending people those large distances into space. Okay, so let's move on to the history of Mars. Okay, so a little history about Mars. Mars, of course, is one of the most well-known of the planets, even from antiquity, back all the way to the Greeks and the Romans and the civilizations in Persia, and even China. And so it's had a great deal of attention. Now, one of the things is that as people were thinking about aliens on other planets, particularly after books like Jules Verne's From the Earth to the Moon, and the science fiction that was being written around the turn of the century, of 1900. Mars began to have a more of a prominent place in our culture. We thought there might be life on Venus. We thought there might be life on Mars. And so people tried to study that. And as telescopes became more powerful in around the 1900s and into the 30s and 40s, before they became the monstrosities that they are today, people studied Mars in great detail. And it turned out that an Italian astronomer had seen what he thought were canali, or channels, that were from possible running water, say rivers and things like that. Percival Lowell, an American astronomer who built the telescope and the observatory, Lowell Observatory up in Flagstaff, Arizona, became very interested in these canali, which he translated into canals incorrectly. And so he thought that this was evidence for, Martian-made, intelligent being created engineering projects. And so he started to fancy that he was able to see these channels, or canals, I should say, on Mars, and thought it was due to a civilization, and even surmised that it was a civilization that was trying to have these great engineering projects to move water around because it was basically a dry, deserty planet. It was a very interesting proposition. So H.G. Wells took this. He was also a dramatist and a fiction writer, and delved into dramatic science fiction. And he took this idea and thought about it in terms of this War of the Worlds. And to promote his War of the Worlds book, he made a radio show. And maybe you've heard of this radio show, but he broadcast it on Halloween. And on that night, he programmed it to take place as a regular entertainment type of show. And he introduced his War of the Worlds as news bulletins that were on the breaks, the normal commercial breaks. So he paid for the commercial breaks and he put his news bulletins in there. And he understood that on the other radio stations during these periods, people would surf the radio, trying to avoid the commercials and things like that. And so he had planned it just at that time when everybody would be surfing their radio. So it was very intelligent. And this first little 5-minute blurb was, there was a flash in the sky that came down over New Jersey. We're going to send a reporter out there. We'll get more news back to you later. And he built these up successively from 5 to 10 minutes, and then eventually was saying, "Oh my gosh, there's movement, there's something coming out of it. Oh my gosh, people are being murdered and shot down in flames," and people panicked, and he presented this so much as a series of news updates and news bulletins and broadcasts that people thought it was real. And there were people that committed suicide. There were people who left their homes and fled from New Jersey. It caused pandemonium, and it was really a national phenomenon, if you will. So that's one of the fun things about Mars, is that people have always been afraid of Martians coming to attack us, and H.G. Wells played on that fear beautifully and caused this panic across the United States. So I thought that was kind of fun to be able to talk about. Now, if we talk about Mars today and we compare Mars to the Earth, which I'll do in the next slide, you'll see that it's a lot smaller. It has less mass, and it has weaker gravity. So if we just look at table 8.1, the basic Mars data, we see that it's about 1.5 times further from the sun than the Earth is. And you'll see that it has a perihelion of 206 million kilometers and an aphelion of 249. So there's a difference between its closest approach to the sun, perihelion, and its farthest distance from the sun, the aphelion, of about 50 million miles. Now, to give you a feeling for how big this is, the Earth's distance from the sun is 93 million miles. So this is a difference that is equal to half of the Earth's distance from the sun. So this is a large amount of distance. And so from the inverse square law of light, you can imagine that as Mars is at its aphelion, it's picking up a lot less energy from the sun than it is when it's at perihelion. And this is one of the things that drives the more extreme seasons on Mars. Its orbital period, it takes about 1.9 years to orbit the Earth, so just under 2 years is the length of its orbit. It's only around 3,400 kilometers in radius, and compared to the Earth's mass, it is about 10%, 0.107, about maybe 11% of the mass of the Earth. So it's pretty down there in terms of mass. Interestingly, it rotates on its axis about 24 hours and 40 minutes, which is extremely interesting that a Mars day is just a little bit longer than an Earth day. Now, your weight from the surface gravity measurement here, your weight would be about 40% of what it is on the Earth. Okay, so atmospheric composition. Well, first of all, I'd like to go down to the bottom of that list of the average surface pressure. It's 0.007 bars. Now, a bar is a measure for the pressure on the surface of the Earth. I should say 1 bar is the sea level pressure of the atmosphere on the Earth. That's about 14 pounds per square inch of pressure on your body and on everything else on the ground, etc. So this means the atmosphere is much, much, much thinner than it is on Earth. So that's one thing I want you to realize. But even of that sort of thin atmosphere, which is 0.7% of the Earth's, then you have the fact that it's 95% carbon dioxide, about 3% nitrogen, and about 1.5% of argon. So on Mars, you are definitely going to have a greenhouse effect because you have a very high concentration of carbon dioxide. However, the atmosphere is very, very thin, so the greenhouse effect is actually quite weak. So I love this picture of from orbit of the sun shining down on Mars. You can see a beautiful picture there. And in fact, if we also look at the pictures below, you see the globe, and the red area is high elevation, the blue area is low elevation, and you can see from this that Mars is quite lopsided in terms of its elevation. Now, one of the things that you can see dramatically on the globe to the left are the white areas. Those are, in fact, very high elevation. Those are volcanoes. You see the one in the upper left is Olympus Mons, and then the 3 that are in a row are called the Tharsis Range or the Tharsis Bulge area. And then the other thing on the globe you'll notice is that what looks like a Grand Canyon or scar, that blue line in the southern hemisphere to the right there, that is called Valley Marineris, and it is effectively a Grand Canyon that spans the length of the entire United States. If you look at the map on the right, one thing you'll notice is that the highlands seem to have a lot of craters to them, and the lowlands don't. And this seems to be indicative that the highlands are old surfaces, that they still maintain their craters. And so the southern hemisphere seems to have a higher elevation, be made of a lot older crust that still bears the scars from the period of bombardment. And the north seems to be lower elevation, and it seems that it has been, in a sense, eroded and repaved, if you will, but eroded from the time of the Great Bombardment. And so this is a younger surface. Quite frankly, what we see and understand this to be due to is that the northern hemisphere was covered in an ocean. And we even see along those green areas, people have seen evidence for what are like shoreline features from the ancient past of Mars. Okay, so here's a really nice comparison between Earth and Mars. And there's one more fact about Mars that wasn't in the previous table, and that fact is its tilt. So it spins on its axis, much the way Earth does. It spins on its axis about every 24 hours, a little bit longer, 40 minutes longer. But what I want you to notice is that relative to the direction of the sun, whereas the Earth's axis is tilted about 20.23 degrees, zero point 0.4 degrees relative to the sun and its orbital plane, Mars is tilted almost identically, about 23.9 degrees. And so what you have here is that you have Earth and Mars both being tilted similarly relative to their orbital plane and the sun, and the fact that they both seem to orbit with equal about days, roughly the same length of the day. So that's a very interesting situation. But we want to remind you that the year is 1.9 times longer. Instead of 365 days, it's about 680 days. Don't worry about what a sol is. Well, that's Martian days, actually. That's what they call a Martian day. So since Mars has a little bit longer of a rotation of 40 minutes, it takes 667 Mars days or sols for the Mars to go around the sun. But in terms of Earth days, that's 686 days. That's kind of a fine detail. Remind you that the gravity on the planet is about 40% of that of Earth, and the sunlight is about 45% of that of Earth. But as I told you, that does vary a lot because of the elliptical orbit. And we've talked about the atmospheric pressure. There's the CO2, the nitrogen, and the argon. There is a little bit of water vapor, as you can see, very, very little compared to the Earth. And there's a little bit of oxygen as well. So that is what Mars is like compared to the Earth. So here's the topographic map of Mars, giving you the Martian geography that is the most famous of the various places on Mars. In the upper left, we have the Olympus Mons volcano, Olympus Mons. This is the largest volcano in the solar system, and it basically dwarfs Mount Everest, which we'll be showing you shortly. And the base of that volcano is about the size of the state of Oregon or the state of Arizona, if you will. So it's quite a huge volcano. We also have the Tharsis Montes. You can see those chain of 3 volcanoes to the lower right of Olympus Mons. And so these are 3 major volcanoes that also formed. Now, these volcanoes formed because the hot spots that happened in the magma of Mars during this period of time that the volcanoes formed, the plate tectonics did not exist on Mars, and that we think in the way that it did on Earth, so that the plates weren't moving across the magma fluid or underground. I don't want to call it an ocean, but the liquid molten magma itself. And so this allowed these hot spots to really continue to build and build and build and build and build these single large volcanoes. And so that's the phenomenon on Mars. To the right of the Tharsis Montes, we see the Valley Marineris. This is what looks like the big scar or the rift, almost like a splitting of a fault if there was a tectonic movement of a splitting there. This is an area that was believed to be filled with water at one point in time. This entire length of this thing, which stretches all the way to the very right of the map, is about the length of the United States. And so the Grand Canyon would be not even almost visible on this map as far as that goes. And in the next few slides, we'll talk a little bit about the geology of the Valley Marineris. So again, you can see that there are a couple large scars on Mars. The Planitia in the upper right-hand corner is believed to, it's a low point on the topography of Mars, is believed to be the site of a large impactor. And also the Agre, if that's how you pronounce it, crater down in the lower right, that's green. And you can see its complete ejecta blanket and size. And then, of course, in the south, you see that there are lots of craters left over from the period of bombardment. So this is a montage of Mars from orbiters, and you can see a couple of major features there. One, of course, we'll go back, you can see Olympus Mons to the left. You see the Tharsis Bulge and the Tharsis range of volcanoes, and you see the Valley Marineris. Okay, so I'm bringing those to your attention again because I don't have to point at those. I think you can see where they are now. Other obvious features are we have polar caps. We have a northern polar cap and we have a southern polar cap. And it's interesting that as the seasons change on Mars, it turns out that those caps, when it's their summertime, get smaller. And then a lot of the carbon dioxide and water in the caps go into the atmosphere and migrate down to the southern caps or to the winter cap, and the winter cap grows. And then, of course, when the next seasons change 6 months later, I shouldn't say 6 months, but half a Martian year later, then the northern cap, they exchange their water vapor again, and the summer cap shrinks and the winter cap on the other pole will get bigger. So that's a very interesting thing about Mars. Now, I'm not going to go through a lot of details of all these little X's here for all these different landing sites. I think we did show them a little bit in the previous lecture, but we are going to see some close-up pictures now or from space of some of these main features. Okay, so here we go with Olympus Mons. Olympus Mons is the largest volcano. It's the largest geological mountain in the solar system altogether. And you can see the picture from space there. It is a gigantic area that it covers. It actually covers about the area of the state of Oregon. And you can see the scarps or the cliffs along the edge. So if you ever think about mountain climbing and you think about climbing Mount Everest and what a feat that is, sometime, I don't know if it'll be 100 years from now or 500 years from now, there will be similar expeditions of thrill seekers who will be climbing Olympus Mons. And I think that is a spectacular and exciting thing. The first thing they will have to do is accomplish the cliffs on the side if they're going to come up the southeast side there. But if they come from the northwest, of course, it's a much more gradual climb. And I'd like you to focus on the inset of the up in the upper right there. And I want to compare to you the two largest structures on the Earth relative to Olympus Mons. So in blue, we have our famous Mount Everest, which is the highest spot on the Earth above sea level. And that's about 5.6 miles above sea level. Now, if you, that mountain range is, its base is basically at sea level. You know, it's inland, and when you measure its height relative to its base area, its 0 point, that 0 point starts at sea level. But now let's look at Mauna Loa in Hawaii. Now, Mauna Loa is, from its base, much higher than Mount Everest, relatively speaking. It's 6.2 miles above its base, so another whole kilometer. Now, which is about 60% of a mile. Now, if you have to really consider the fact that, okay, so Mauna Loa above sea level doesn't stick that high, but if the ocean's dried up and you were to say relative to its base, which is the highest, largest, volcano or mountain on the earth, it's Mauna Loa, hands down. Okay. Now, if you look at the difference, how high Mount Everest is to Olympus Mons, you can see that the difference from 9 kilometers up to 27 kilometers. So it's 3 times higher. Now, you know that you need oxygen masks to go up to 9 kilometers when you're hiking Mount Everest, and a lot of people have died attempting this. Olympus Mons is already in an atmosphere that is only 0.7% the thickness of Earth's on average. And when you go up 27 kilometers, you're virtually would be equivalent to going into space. And so this is a spectacular challenge of endurance to try and climb Olympus Mons. Now I have a little video clip down in the corner. It's only about 2 minutes or so. I did not put that on the website. I might go ahead and still put that on the website. It's a nice little picturesque story. So I'll get that one up there. I haven't gotten it up yet. Okay, and just for completeness, I want to show you the Tharsis Bulge region and the 3 volcanoes that are part of that structure. And so here's another picture from space, just showing those. And you can see in the photograph, you can see that scar tissue that you, in a sense, that you to the right as you go toward the limb of the planet, and that is the Valley Marinaris. So um, I think seeing Mars in person would be a very spectacular and beautiful thing, even though it is fairly dead. It still has a stark beauty of all its own. Okay, so let's talk about Valley Marinaris for a while. Um, you can see where it's located on the planet by the blue oval that I've shown, and then the arrow pointing to that shows a close-up, and you can see the overall structure. There's a lot of cliffs, a lot of layering. Interestingly, unlike the Grand Canyon, which has these horizontal sedimentary layers, you don't see a lot of the horizontal sedimentary layers for Valley Marinaris. You see more of these vertical scars of things that have crumbled down from erosion. It's a very different type of geology, and I'm not sure that it's really well understood yet. So if you move upward from the lower right picture, you see the circled area in that one, and you can then move up to the upper picture on the right, and you can start to see a much higher resolution image of that vertical scarring on those scarps. Now, I don't know if everybody knows this, but we have higher resolution images of the surface of Mars from space than we do of the moon, just to give you an idea of how well Mars has been studied. Again, another beautiful picture from space in the upper left, showing you the sun in the background and the shadow relief of the scars tissue of the. That's what it looks like to me. It looks like some kind of splitting of the surface that happened, like a fault line, if you will, that created this Grand Canyon-like feature. Now, earlier I mentioned to you that it was about the length of the United States, and so in the lower left you see there's a picture of the United States overlapped on top of Valley Marinaris, and it would be the Grand Canyon would be one little tiny dot in that picture, and so you can get a feeling for how incredible this geological feature must really be. So now this is our last little stop along the way. This is the Southern Highlands. The Southern Highlands, if you remember the global map of Mars that I showed earlier in the lecture, is sort of in a transition region between the North lowlands and the older areas in the south. And what's interesting about this area is that there's a great deal of evidence for running water in the past. So if you look in the lower left, you can see one of the older images that we have, and you can see that there's some cratering, but the craters have been filled in, and this would be indication of seepage from water, or and filling in, as if they were filled in by lakes, or the fact that there was a lot of erosion, also indicative of water. But you can also see what appear to be small little pathways that look like riverbeds, and this is an indication of flowing water. Now, if you look to the right, you can see a great deal of erosion, and you can see what looks very much like river deltas and the carving out of waters. Okay, and this is an infrared. It shows very, very strong evidence of different types of mineral deposits in these different colors. You could see, for example, the crater there that's left over where the water has moved around, and at one point that may have been an island. There are features like this all across Mars in all kinds of different locations. They've taken rovers, they've scraped up the rocks, they've measured the minerals. There are rocks there that definitely show the same behavior as river rocks do on Earth, that the minerals are deposited into the rock in a way that only happens when you have them embedded in the presence of water. So on and on and on, the evidence for water on Mars is very, very strong. There's no doubt that Mars in the past was very active in terms of water, and therefore had to have an atmosphere, because to keep water on the surface, you have to have air above it to keep the pressure there to allow it not to just evaporate into space. And to keep an atmosphere, you need a magnetic field, because you need to shield the atmosphere itself, the air blanket, if you will, from the solar wind, and which would eventually heat it up and strip it away, which we're going to talk about later in the lecture. So Mars had to have had a magnetic field, it had to have had an atmosphere, and it definitely had running water. And the reason it had to have those others is because it had the running water. You can't have running water without the atmosphere. You can't have the atmosphere or keep it without having the magnetic field. What happened to all of that? Well, that's one of the things that we'll be talking about a little bit later. Now, I'm going to talk to you about the Martian seasons. And this is these next two slides are slides that, if you're getting a little burned out, take a little break and come back and be a little fresh, because this is some important material, and there's a little daisy chain of logic that is, in a sense, required to be able to sort of articulate this. Okay, having said that, let's push forward. Let's think about the seasons on the Earth. Now, misconception. Let's get the misconception out first. The seasons on the Earth are not because the Earth's orbit is elliptical. Now, yes, the Earth's orbit is elliptical, but it's only 3% out of round. So the difference between the Earth's closest approach to the sun during its orbit and its farthest approach, its perihelion and its aphelion, is only a 3% difference. Okay, so it's a very, very small change. We almost have a circular orbit. So it's not because it's closer to the sun or further from the sun. That has nothing to do with the seasons. It has to do with the Earth's tilt relative to the sun. And I want you to notice something about that center image and the tilt of the Earth as it's being shown going around its orbit. So you see the orbit, you see the arrows telling you the direction of the orbit, and then you see that the Earth's axis is tilted. And one thing you should notice here is that the tilt of that axis does not change its orientation in space. Even as the Earth moves along that blue orbital line, the axis is always pointing upward and to the right. And in fact, if you could see this in 3 dimensions and look straight up that axis, that actually points to a star, which is just circumstantial that it points to a star. And we know that star is the North Star, also known as Polaris. So for there to be a North Star, that means the Earth's tilt, or it's the direction its axis points in 3-dimensional space, must never, ever change. Okay. Now, it's not completely and totally fixed for all time, but for our sake of our discussion, let's consider that it is absolutely fixed for all time, just to simplify things. Okay, so you can see now, let's go to the Earth on its orbit to the left there, which is labeled summer solstice. At that point in time, you can see that the sun is on the side of the Earth where the north axis is sort of pointing in its general direction and the south pole is pointing away from its general direction. And so what happens is that the sun is having very direct sunlight directly onto the northern hemisphere, and its light on the southern hemisphere is more of a grazing angle. And so they're trying to show you that with the little outset picture. So if you go to the picture of the summer solstice Earth, and you follow that little beam, that triangle, white triangle up to the left, in the upper left of this center panel, you can see that the sunlight and the yellow arrows are coming in very directly to this individual standing in the northern hemisphere. There's the line of the equator, and below that is the other individual, and you can see that they have a longer shadow because that light is actually at a much more grazing angle. Now, what does this mean? So let's go to the panel, on the two panels to the very left, showing you the summer in the north and the winter in the south, which for fun I turned upside down. Okay, so in the north, you see the sun is high in the sky and the sun is coming down at a fairly direct angle, and that's being shown by this lower panel with the yellow circle as the sunlight. So what we're saying here is that the amount of energy contained in a little circle on the Earth is relatively high because the light's concentrated. If you go to the southern hemisphere during this June-July period, the sun is much lower in the sky, and so you can see that the light shown by the yellow arrows there is at a much more grazing angle, and the light is distributed now over a larger area rather than the tight circle in the north. It's more distributed in an elongated circle, and it's not as bright. They're showing it to not be as bright, and therefore the energy density of the light on the Earth in the south during this month is lower. And so really that's what it comes down to. In the north, the energy density on the hitting the surface is higher, and the energy density, because of the grazing angle, is much lower in the south. And so we have summer in the north because we're getting more energy, and winter in the south because we're getting less energy density. So that's why we have the seasons, say, for example, summer in the north and winter in the south. Now, move along the Earth's orbit, go back to the middle image, go along the blue arrow path of the orbit, and let's go all the way to the winter now. And you see the tilt of the Earth has stayed fixed in space. And now what's happening? Well, if you go up to the upper right corner where it's showing the sunlight coming into the Earth with our two individuals, now the person in the south has the shorter shadow because the light is coming more directly to the southern hemisphere. And the person in the north has the longer shadow because the light is coming more at a grazing angle. And then again, if we go to the images labeled December and January on the right-hand side, in the north, what do we have? The sun's low in the sky, the grazing angle is high. We see that the energy density is spread out more. The angle coming in is spread out. And then if we go to the south, we see that the sun is higher in the sky, the angle is more direct, and the energy density is higher. And so we have summer in the south and winter in the north. And so this happens as we cycle on and cycle through as the Earth goes around its orbit. Okay, so this is basically what causes the seasons. And again, at the very, very bottom of this slide, I show basically a summer sun, and this is down in the left-hand corner, a summer sun and a winter sun, showing you that the light is more concentrated in the summer and less concentrated in the winter. And that can flip north or south depending upon where the Earth is in its orbit. And then showing you basically how the rays come in and fit into a smaller area, therefore depositing more energy on the surface of the Earth in a given area of Earth Whereas in the bottom here, where you see the winter tree and the December sun rays, of course, they're using northern hemisphere months. So December would be winter in the north, and the angles are coming in, and that light is distributed, or I should say diluted, over a larger area, and therefore there's not as much energy, and we call that winter. Okay, now, this is the big slide on seasons and seasons on Mars, and it contains a great deal of information, so we might be paused on this one for a few minutes. As you consider the way that seasons behaved on the Earth, one thing that I would like to remind you is that the Earth's orbit is pretty close to circular. Now, we learned from Kepler's second law and Kepler's first law all about how these orbits behave. So I'm going to talk about that very briefly. The first thing about Kepler's law was that the planet orbits are ellipses with the sun at one focus. Okay, and so that's true for both Earth and for Mars. It just turns out that Earth's orbit is very, very close to being circular. Now, Kepler's second law, we learned basically that the closer the planet is, as it goes along its path and it's near perihelion, near the closest approach to the sun, the planet is moving along its orbit at the fastest rate, at the highest speed along that path. And as the planet moves to its aphelion, or its furthest point from the sun during its orbit, as it's moving along the path there, it's moving the slowest, or at the slowest speed along its orbit. And so with a planet that's highly elliptical, as it's near perihelion, it's going to be moving more rapidly along its path around the sun. And when it gets to perihelion, it's going to be going at a much slower pace along its path. Now, the thing about the Earth is that its speed doesn't vary very much along its path. And that's because its orbit is so close to being circular. So in a sense, if you want to simplify things, it's not 100% true. You could think of the Earth as being on a circular orbit, and that its speed actually was unchanging as it goes along its orbit. Now, it's not perfectly true, but you can approximate it that way. Now, because it is close to being that way, here's the point. The seasons will have the same length all year long, okay? In other words, when you have some summer in the north, you will have that for, say, 3 months, and you'll have 3 months of winter in the south. 6 months later, when you go and you have summer in the south, it'll last 3 months, and the north winter will last 3 months. So what I'm saying is that as the Earth goes around the sun, the seasons of what's in the north and the south will be the same duration as they are 6 months later, but they flipped hemispheres. So that's the other thing. The other thing is that the seasons don't become extreme from one another because the Earth, is always almost the same distance from the sun. The strength of the summer in the south is equivalent to the strength of the summer in the north. Likewise, the coldness of the winter in the north is equal to the coldness in the winter in the south. So because the Earth's orbit is so close to circular and the speed at which the planet moves along its orbital path is fairly fixed and fairly constant, you have two things happen. Because the orbit is so round, the intensity of the seasons basically are a mirror for north and south hemispheres. And because it's so round that the speed along the path is fairly fixed, the duration or the length of the seasons of the north hemisphere versus the southern hemisphere are roughly the same. So we have these very equal seasons on Earth. That's the main point that I want to talk about, is that on Mars, you don't have that. On Mars, you have a much more elliptical orbit. It's 9% out of circular rather than only 3%. And this is a substantial difference. As I told you, Mars actually, from its perihelion, to its aphelion, that's a difference of 50 million miles, which is a distance that's equal to half the distance from the sun to the earth. So that's a large distance. And what we find is shown on this particular graph. Now, similar to our Earth orbit, we've got now an orange arrow going around for the orbit, and then we have the direction of the spin axis of the planet Mars. In this case, you could think of this as the north pole is the arrow pointing upward to the right for the spin axis. And again, it's fixed in space as the planet moves around in the orbit. So let's consider what's going on here. First of all, let's start on the left-hand part of the diagram where the planet is at aphelion, farthest from the sun. And you can see here we have the northern hemisphere is summer and the southern hemisphere is winter. Now, along this part of the path, the planet is moving the slowest along its orbit. That means, folks, that when it's at this stage of the orbit, the seasons are going to be much longer than they are in other parts of the orbit because the planet's taking its sweet time out here. So what do you get? You get long summers in the north and long winters in the south because that's the configuration you have at aphelion, okay? Now, the other thing that's happening out there is that the sun is further away from Mars at this point in time when Mars is in its aphelion along its orbit. Therefore, from the inverse square law of light, the intensity of the light is lower. Okay, so let's think about this for a second. You're Mars, you're at aphelion, you have a northern hemisphere summer and a southern winter, and they're going to be longer. And now, because you're at the farthest point from the sun in your orbit, your summer is going to be pretty mild, right? It's going to be a relatively cool summer because you are far from the sun, the intensity of the light is lower. So guess what you get on Mars in the north? You get long, mild summers, okay? Okay, but what do you get in the south? Well, you get long but very cold winters because you're farthest from the sun and you're moving the slowest and you're getting the less light from being farther. So over here on the left-hand diagram at aphelion, north summer, it's long and it's mild, and winter, long and very cold. Now let's move to the right-hand side of the diagram where we're at perihelion. Again, notice that the tilt of the Mars has not changed, and now we're at a situation where we are closest to the sun and we're moving the most rapidly along our orbit. That means we're going to be spending less time along this period, this point of the orbit. We're going to spend less time at perihelion. Now, at perihelion, what do you have? Well, you have summer in the south, as you can see, where you have the more direct sunlight, and you have winter in the north. Okay, these are going to be shorter seasons because the planet is moving through this area of the orbit most rapidly. And get this, in the north, the winter is going to be mild because the planet is closest to the sun and therefore getting the most light energy from the proximity inverse square law effect. So you get a short, mild winter in the north at perihelion. And what do you get in the south at this time? When it's summer, you're getting a very, very hot, short summer. So you get a short summer, but it's very hot. Okay, so I will ask you now, which hemisphere would you want to hang out on, north or south, if you were going to go on the planet Mars? And I'm going to tell you, I would much rather hang out in the north because basically the winters are short and mild and the summers are long and mild. And you know what? That sounds pretty awesome to me. If you're down in the southern hemisphere, you're going to have long, frigid winters and you're going to have short but hot summers. Okay, so I'm going with the north. Anyway, that's the way the seasons work on Mars. So you're at aphelion, you have north summer. If you can remember just that rule of thumb, When you're at aphelion, you have northern summer. Then you can piece together the rest of it from all of the logic. And the logic is that the Martian orbit is not round, it's elliptical. And therefore, at aphelion, you spend more time in that area of the orbit. And at perihelion, you spend less time. Also, at aphelion, you're farther, so you get less light energy. And when you're at perihelion, you get more light energy. And from just that information, you should be able to piece together the Martian atmospheres by a series of little logical daisy chain arguments. So you can choose to memorize these orbits. You can choose to memorize these hemisphere seasons. Well, north is short summer, and blah blah or whatever. I said that backwards, but anyway, you can memorize this stuff, or you can try and understand it, and then be able to piece it together just by thinking it through. And my advice to you is to always err on that side of that. That's the kind of thing that's going to help you no matter what you do in life. And that's my little soapbox of advice on that. So I hope you learned a little bit about why the seasons on Mars are different than they are on Earth, and exactly how the seasons are working, if that's not something that you had known before you had entered this class. Even though the geological record definitely shows that water was quite abundant on Mars, and that the planet was partially covered with an ocean, mostly in the northern areas, there's a global stretching of seashores. There's, of course, river deltas that clearly fed into the oceans, much like the Mississippi Delta down in Louisiana. So there's all this evidence, but the conditions for Mars to have this ocean are still a little bit confusing to us. And so I'm going to give you some information here in this bulleted list, which kind of, in the end, shows that there's a little bit of a quandary as to how this could happen. And some of this has to do with the evolution of the sun, which will be talked about in much more detail in future modules. So number one, for liquid water to have been stable, that we've already talked about in detail that there must have been some atmosphere, because you need atmospheric pressure to hold the water from evaporating. The lower the atmospheric pressure, the faster the evaporation rate of the water. So for the ocean to be stable, we would realize that that pressure would need to be about 3 times of that on today's Earth. So that would indicate that Mars had indeed a very thick atmosphere. All right. And then it could be that greenhouse gas contributed to keeping the planet warm, so that it would be able to have the conditions for liquid water to be on that. Now, that would have to be due to carbon dioxide. However, to get the temperatures that are required, because today's Martian temperature is, I think, 5 degrees below Celsius or something like that, you'd need about 400 times the current carbon dioxide level. So again, you could get that by having a thicker atmosphere that's dominated by carbon dioxide. So that's not really the big quandary. But the quandary is, how do you get this large atmosphere full of so much carbon dioxide and keep the planet warm when bullet number three, the sun was 30% as bright during this era that the atmosphere existed. It's called the Nochian era, and it's basically the first 200 or so million years of Mars. So with only 30% of the sunlight coming into the atmosphere of Mars, because as the sun ages, it gets more luminous and brighter. So back in this period, when the solar system just formed, the sun was only 30% of its present-day luminosity. The energy required to warm the planet such that liquid water could exist on it was just not as abundant. I'm sorry, it was not as high. The energy requirement was, what am I trying to say? I'm trying to say the sun was not providing enough energy that would be required to keep the temperature pumped up on the planet's atmosphere enough for the liquid water to exist. So that's really a quandary. We've already discovered we need a lot of atmosphere with a lot of greenhouse gases to make this work. So the solution to number 2 and 3 may be that there were a more efficient greenhouse gases than carbon dioxide, and one of those is methane. Methane is an extremely uh, efficient greenhouse gas. It absorbs a large band of infrared light. We just simply don't know about the methane on Mars. And one of the main things being studied on Mars is how much methane does it have? And does the methane vary seasonally? In other words, is some of it trapped and does it come up in a seasonal way through some kind of subterranean atmospheric methane cycle? So people are studying that in great detail. Now, it would seem that Mars could have been completely covered with water to about tens of hundreds of meters, and we definitely know that it wasn't. We seem to have the evidence that it was only about a third covered and mostly in the north. So the thing is that the volcanoes on Mars, if they were really, really active, they probably could have produced enough of this water vapor that they could have, um, you know, generated enough of an ocean to cover the whole planet. So somehow it seems that this water vapor did not cycle back down onto the planet, but perhaps probably was escaping the planet. And we'll talk a little bit about how that could have happened in a bit in the next slides or so. So anyway, I guess what I'm trying to make my point with here is that we really don't understand the climatic history of Mars, particularly the period in its very early days when it would have been a habitable planet, quite literally a habitable planet. If we had brought some bacteria there or some extremophiles, they probably would have done just fine. Okay, so some questions that we have to really ask ourselves is why was Mars warmer and wetter in the past? What caused Mars to change from that? Is Mars currently habitable, and is there evidence for life on Mars? So we'll talk about those things a little bit in the coming slides. Okay, continuing our misunderstanding, if you will, of the climatic history of Mars. I say that as a joke, but as usual, it doesn't stop us from hypothesizing what happened. And with science, that's what we do. We take guesses as to what may have happened, and then we collect more data. And the data either, as we learned in Module 2 way back when, the data either support our hypothesis, from which case we continue on to collect more data and test other predictions, or the data demonstrate that the hypothesis must be revised entirely, and we start with new hypotheses. So basically, there's a couple hypotheses as to what happened to Mars. One is sort of the natural path, and that is what this slide is about. And then the next slide will talk a little bit more about some possible catastrophic things that might have happened to Mars. Now, the natural paths are usually considered to be the more likely channels because you don't need any special one-off events. But it may be that Mars had a special one-off event in the same way that Earth had a special one-off event that created the moon. So, with Mars, this slide really is going to focus on the fact that Mars is smaller than an Earth-like planet, or smaller than Venus, smaller than Earth, and its size, in particular, its capacity to hold a heat reservoir, is going to be the key to this particular discussion. So in this slide here, I say that heat loss through the surface of the planet, so heat loss rates scale with surface density, and the amount of heat scales with the volume. So what you can think about is a planet is a sphere, and that sphere has a certain volume, and in that certain volume, you can contain so much energy, what you might call heat. But you basically are containing a certain amount of energy, and the bigger that volume is, obviously, the more the more volume you have, the more energy you can hold in your heat reservoir. So, and the volume goes up with the radius cubed. So basically, 4/3 pi r cubed is the volume of any sphere. And so the volume goes up with the radius cubed, which means as the planet's radius gets bigger, the amount of energy that it can store in its heat as a heat reservoir goes up with the radius to the third power, which means it is increasing pretty rapidly as the radius goes up, the volume and the heat reservoir. However, that heat is going to escape out of the surface slowly. So you could think of the surface around the sphere of the planet to be sort of this filter through which heat is then able to escape. And so there, the total amount of heat that can escape in a given amount of time depends upon how much surface area it has to escape through. So the more surface area that it has to escape through, the faster is the rate at which the heat energy can escape the planet. And vice versa. If that surface area of the planet is small, then the rate at which it's going to radiate its heat out to space will be smaller. So the surface area goes as the radius squared. So surface area goes as 4 pi r squared. Now, if you want to know the amount of time that it will take for a sphere with a certain amount of volume and heat in it to radiate all that energy into space, you take the rate at which it can go out of the surface and divide it by the amount of energy that you have. So basically, when you do that, it's equivalent to this equation in the upper right of the surface area, which is the rate at which it can escape, divided by the amount of energy, which is the volume containing that. So when you do that, your 4's and your pi's cancel out, and you get basically 3 divided by r. So who cares about the 3? The point is that the r is in the denominator, which means that the rate of, or I'm sorry, the time, that's what we're calculating here, the time that the planet can hold on to its heat basically is going to go up as the radius of the planet goes up. Okay? And so the rate of loss goes as 3 over r. And so that means that the bigger the planet, the slower the rate at which it's going to lose energy, and therefore the longer that it will maintain its and contain its heat energy. So that's a long argument about the way that planets of different volumes and different surface areas will contain and retain their heat. So just to summarize that long argument again, bigger planets will stay hotter and maintain their internal heat for longer periods of time, and smaller planets will lose their heat more rapidly and therefore cool down in a shorter time frame. And so Mars is a much smaller planet than Earth, and therefore it's going to lose its heat much more quickly than a planet like Earth. And so Mars, it's calculated, would have cooled down fairly rapidly because it doesn't have very big volume, so it didn't have much heat energy to start with. And then it had this surface area at least large enough that it could radiate that little bit of heat it had fast enough that it would have cooled down relatively early in the solar system. Okay, so that's what all of that stuff across the top is. The bottom line is what you want to walk away with this slide is in the yellow with the red box around it, that it cooled off toward the end of this period, say in about several 100 million years. That means that the core would cool, Okay, and you know that if the core is cold, then it's not able to have hot charged particles moving around that creates electric current, which generates magnetic fields, and then the dynamo effect that happens in the earth. Um, and so, if that happens, guess what? Mr. Magnetic Field is going to shut down. And if magnetic field shuts down, then you're basically going to lose the outer shield around the planet. So, in addition to your core uh, solidifying and then your mantle cooling and volcanism shutting down and any of that geological activity shutting down with time, you also lose your magnetic field. Now, the diagrams at the bottom are basically showing you, once again, what a magnetic field around a planet like early Mars would look like. And in fact, it would be very similar to the Earth. And so the solar wind particles would get channeled away from crashing into the atmosphere, except for the very highest energy ones that might, cause northern or southern lights, aurora borealis, in the polar regions of Mars and its atmosphere in those days. Okay, but today Mars doesn't really have a global atmosphere, and we'll talk about that in a minute. Um, and so, without the global atmosphere, you basically have a situation where the charged particles in the solar wind can crash directly into the atmosphere. And this turns out is one of the reasons we think that the atmosphere got stripped from Mars. Okay, and so basically, I do have a movie about the magnetic field here, and in that movie, um, you basically have a small tour of Mars's magnetic field from the point of view of a scientist at MIT who studies it. And basically, and here's the magic password thing for the day, Mars has a magic password, weak and crazy mixed up magnetic field. And that is very much the truth about the magnetic field of Mars. It's patchy, it's all around in the very different corners of the thing. And so, if you didn't understand, that magic phrase was the attendance phrase that you're supposed to use for your attendance quiz. So you're going to see in the movie they talk about the fact that different locations on Mars you find little patches of magnetic field that are residual, and it's a very fascinating little movie. Okay, so um, the natural idea that the planet cooled, lost its magnetic field, and then the solar wind was able to strip away the atmosphere, and then basically Mars became what it is today. There's also some other ideas. Um, so the other ideas means that basically, as you lose the ability to have volcanoes, you don't have the ability to replenish the atmosphere as it might get stripped by the solar wind or get stripped by any other mechanism. So that's the reason that the atmosphere ends up going away, is because you don't have anything to continually generate new atmosphere. Excuse me. So no volcanoes means no greenhouse gases. The planet's not going to be warmed. It's going to not replenish the atmosphere. Everything's going to cool down, and you really have this chain of events that we were talking about. But other possibilities is you could have had a shock wave from a huge impactor or from multiple impactors toward the end of the period of bombardment. Now, the Nochian era really begins after the period of bombardment and then lasts for another 250 odd million years. Um, so it would have had to have been sort of after the period of bombardment ended, but that you still had the occasional large asteroid come and hit. But there is some theory that there was one large, huge catastrophic impactor, and it's one of the videos that you're supposed to watch. In fact, it's the first one up there under that black line that divides the slide. The first video, due to asteroids question mark, is the first video. of on here, this page. And so the idea then is that shock waves could have come down, and the image in the bottom there that shows an impactor, this is image A, uh, this could create a shock wave which would blast material outward from the atmosphere. Now, if it was a lot of moderate sized impactors, meaning, you know, things that were like the KT impactor, which actually are pretty big, if there were a lot of those that hit over those 50 million years or so toward the end of the Nochian, then it could have, like, you know, knocked away 10% of the atmosphere at a time or something like that, and basically shut it down. But that would have that would only really work if the planet had cooled down at the same time, or it had already previously started to have its geology shut down. But the idea that NASA has for the large impactor is that this was, you know, something that happened to the Earth when it created the moon, and it basically wiped the atmosphere away and shocked the planet and cooled it and allowed it to, you know, become geologically dead. So that's going to be one of the ideas there. And even though there's the idea of multiple shock waves from multiple impactors, the NASA theory that's favored is one of a very large impactor that came on and knocked out, basically just knocked the socks out of Mars. Okay, the other idea is that if it cooled down, instead of it being the solar wind that really stripped away the atmosphere, one of the other things that might do it is also ultraviolet light. But anyway, picture B is again more about the solar wind particles stripping the atmosphere away. So these are the possible mechanism, and there's another video called The Death of Mars, which is a kind of a summary of everything that we've been talking about, which is really quite good. And these movies have very good graphics, and of course it's Mars, which is the planet of war and drama. So of course the music's always dramatic, but it's fun to watch. Okay, so the lack of water itself really might have been due to this process of the solar wind particles stripping away the hydrogens and the oxygens from each other, breaking those water molecules apart, from which the hydrogen would escape. Oxygen might get bonded to carbon, make carbon dioxide, a process very similar to what happened on Venus, except Venus, being a larger planet, didn't lose all of its atmosphere. Because Mars has such a weak gravitational field, it could not hold on to its atmosphere as readily. Okay, all right. And the other thing is, you might always ask yourself the question, you know, well, why is Mars red? You know, why does it always look red? And it turns out that there's a lot of iron in the rocks, and they've all been oxidized and rusted from this leftover oxygen from the dissociation of water molecules, where the hydrogen left and the oxygen either bonded with carbon to become carbon dioxide or became oxidized into the surface of the planet. And so literally this planet's surface has been highly oxidized, and that's kind of an interesting thing that's unique about Mars. Okay, so here's our summary slide for what we've been discussing, and it's almost just worth reading at some level. So I think that I would encourage you to read this, and I'll try to not read the whole thing to you directly, but we basically said that Mars's size was very important. That would be the first line up there. The second thing was that even though it had volcanism and outgassing, so that it could, put a lot of water vapor into the atmosphere and make a atmosphere early in its history, it turned out, because of its size, it was too small to contain or maintain that internal heat without letting it escape to space. So this internal heat loss would have been one of the reasons that Mars evolved the way it did. As the interior cooled, you're going to have a hardening of the inner core. You're going to have a shutdown of the magnetic field. You're going to have a shutdown of volcanism, a process that can replenish the atmosphere, with the loss of the magnetic field, you have charged particles from the sun able to strip the atmosphere away. Okay. We do believe that if Mars had been about the size of the Earth, that it may still today be a habitable planet. That's very interesting. Um, Now, it could be that because it was small, the other thing that sealed its fate was its distance. So, for example, what if Mars had been the distance of Venus from the sun? What if it had been closer to the sun than the Earth? Then that may have had a way of keeping the planet warmer that would have helped it. It's hard to figure out that without computer models. I don't know the answer, but that's just a hypothetical question that's of interest. Okay, and the bottom line is that Mars is 1.5 times further from the sun than the Earth, and it could have been that that weaker amount of sunlight was part of what sealed its fate. We believe today that it's possible that there's a lot of permafrost and frozen water uh, on the surface of Mars, and maybe even liquid water underneath the surface in caves, which is something I'll be talking about in the next slide. Now, interestingly, I mentioned the polar ice caps. The polar ice caps basically are carbon dioxide and dry ice, but they tend to have also cores at the bottom of them. They're deeper ice, which is water ice, and so there is a lot of frozen water on Mars in terms of the polar ice caps. We really haven't explored Mars well enough to know about all the various places that permafrost and water exist on Mars. So that's something that hopefully will happen in your lifetimes. So the question might be then, is Mars habitable? I would say that if you were to put some life forms on Mars today, that they could definitely some of them could survive. And in that sense, we would have to say yes, that Mars is a habitable planet. It's sort of marginally habitable in terms of the fact that it would have a fairly narrow ecological niche for its life forms, and they would have to be somewhat extremophiles, and extremophiles in the cold sense. So the types of things you see growing in the rocks in the polar ice cap areas of Earth and things like that. However, life can persist a great deal in caves and become there's tremendous ecosystems on the earth that exist in caves. Now, caves are natural areas where liquid water on Mars could also be congregating, and extremophiles that are similar to the ones that live in Earth caves could be living on Martian caves. So, a lot of people are doing research by sending robots into Earth caves and trying to figure out how to get them to learn how to navigate, how to collect data, how to send the data back, and do all of these things so that they can practice it on Earth and then send some robots to Mars. And hopefully, we can find some caves and we can get people sending caves in there. Um, it turns out that up at New Mexico Tech is a professor named Penny Boston who's become quite famous pushing this kind of work. And she's actually taken University of New Mexico and University State graduate students, I'm sorry, New Mexico State and University of New Mexico graduate students on these field trips with her to look for life and study how you would study life on Mars in caves. They've done a lot of caving, and Penny Boston has now become the director of NASA's Biology Institute. So this is a very, very exciting area that could exist. And so I'll quote her here. We have thought about what life might look like on the surface of other worlds, but in light of the huge biodiversity of microorganisms in the subsurface of Earth, the subsurface in general, and caves in particular, will be an important place to look for life on other bodies. I believe that there may be many planets, including Mars, where life only on the planet is restricted to the subsurface. So I think we'll be talking about the moon Enceladus around Saturn and its water ice geysers and the fact that it would have the energy budget and liquid water for life. And we also will be talking about Europa, one of the moons of Jupiter, which has underground oceans and also probably is a habitable body and may have subsurface life. Okay, so for this slide, I threw on two videos. One of them, How to Send an Experiment to Mars, is really an interesting video. I don't have a link to it. I'm not going to put a link to it um, on Canvas, but if you want to watch it, you can just cut and paste it from the notes and put it in your navigation bar. It's a really nice story about planning the mission, launching the mission, monitoring the spacecraft, getting it to go into orbit, getting it to land on the planet, getting it to send back the data, how you do all that. And so if you're interested in those kinds of things, particularly a career of that nature, it's a good short movie on that kind of stuff. The second one is what needs to be figured out to send humans to Mars. Now, I put this as an optional movie on the modules on Canvas. It's a very fast-paced lecture. It's chock full of information. It's high density, but it's a very, very instructive presentation of what would be required to send humans to Mars. And it's quite an engineering challenge. It's quite a medical challenge in that sense. So if you're interested in that kind of thing, I would also recommend giving that a watch as well. Okay, in the past, when I used to talk about is there evidence for life on Mars already? I mean, do we already have evidence for life on Mars? I had a series of slides on the Viking missions, which were the first two spacecraft and landers, I should say, to land on Mars in the 70s. And they had a special experiment that was designed, four experiments actually designed to look for life on Mars. And so I used to go through each experiment, talk about how it worked, what it was looking for, and blah, blah, blah. But I decided to drop all those details and just tell you the basic result was they did these four experiments, and three of them conclusively came up dry, meaning no signs of life. One of them came up suggestive of life in that there might have been some respiration products in the soil from this particular experiment. And then it turned out that they did another follow-up part to that experiment, which made the experiment ambiguous. So that fourth experiment actually left people with the ambiguity of whether there was life on Mars. Now, you talk to some scientists who study Mars in detail, especially astrobiologists, and they're convinced that we could find life on Mars and that we should definitely try. Now, I'm going to tell you a story that shook the world in the mid-1990s, and it's the story of ALH 84001. So I know that rolls off the tongue, but you should get used to that name. ALH for Allen Hills, 84 for the year 1984, and 0001. Basically, what do you find? Where do you go on Earth to find little asteroids that came from the planet Mars? Well, it turns out that when impactors hit Mars, they kick up rocks and they jettison them to escape velocity, and out into the solar system they go. And then it might travel around for I don't know. 16 million years wandering the solar system, for example, ha ha ha. And then after that happens, it might somehow get trapped in Earth's gravitational field and come down to Earth. Now, a lot of these asteroids would hit various locations of the Earth, but it turns out that they're well preserved at the South Pole. So where do you go to find these things? You go to the South Pole. So off to Antarctica people go. There's an area called Allen Hills in Antarctica. 1984, there was an expedition, and the first Martian rock that they picked up in 1984 in that expedition, they named ALH 84001. So they brought it home, they put it in a museum, and the curator stuck it in some box and put it in a drawer down in some basement, and there it sat for about 10 years. And so finally it got pulled out in around 1994, and it turns out that somebody thought that they found signs of fossils in this meteorite. Okay, so this little timeline down below basically gives you what we think is the history of ALH 84001. So it's a 4.5 billion year old story, and this story has its pinnacle in August of 1996 when it's discovered this. Now, here's a picture in the upper right corner of the rock, which is everything's to do about. The little block in the lower right hand corner is a sugar cube that gives you the idea of how big it is. If you look at it close in figure B down at the bottom, you see these little carbonate globules, and carbonate globules are the kinds of things you see in rocks that have been filtrated by liquid water. Excuse me. And so these globules have been dated back to 3.9 billion years ago. And so that's why we say in the timeline that it was infiltrated by water back in those times. So here's a rock that had water in it that has traveled through the solar system. And so what did we learn about it? Well, people thought that they saw these little, crystal magnetites aligned like little spines. Now we see these crystallized magnetites aligned along the spines of very, very tiny, tiny critters all over the Earth. And it turns out that their little magnetic spines align them in the Earth's magnetic field so that they basically always swim in the correct direction to find the surface of the water, for example. And it's interesting because the alignment of the direction that these things will swim on Earth is such that they're aligned with the North Polar region if they're a Northern Hemisphere critters, and if they happen to be born or evolve in the Southern Hemisphere, the magnetites point in the opposite direction with respect to the way they swim. So it's very, very interesting aspect of life on Earth that these little magnetite chains, backbones in a sense, are critical for certain life forms. So these little beads were found, as you can see in the left-hand panel, in the rock using an electron microscope. And they basically had similar size and shape to those of bacteria on Earth. So that was one of the things that really got people excited right off the bat. The other thing about the carbonate globules moving to the center is that they have alternating layers of magnesium and iron and calcium-rich carbonates. And if you remember our discussions of stromatolites, this is the kind of thing that happens when you have bacteria colonies that line up in layers and cause these stratifications. And so since this was something that was common to biological activity on the Earth, it was believed that in fact, perhaps, that this process had taken place in this rock as well. Okay. Now, the thing is that it's possible that these have non-biological origins as well, and that turns out to be now the favorite hypothesis. Oops, I gave the punchline away. People don't believe it had life in it. Okay. The other thing are these little small, on the very right-hand side here, these small rod-shaped structures, little segments. Again, they are similar to what you find in Earth bacteria. Unfortunately, for the people who were proponents of finding life fossils here, these were about 100 times smaller than that of life. But people have talked about the idea of something called nanobacteria, called nanobes, that have recently been discovered on Earth. But it's just believed that in the modern day that these were not the equivalent of nanobacteria. And so in the end, ALH 84001 caused a huge splash. The scientists became very famous for a time being while people debated this. I can tell you at the universities I was at Penn State at the time doing my postdoc, and it seemed that every week a scientist was coming through and people were having debates, public debates and private debates, departmental debates about whether this existed. And it was a very, very heated topic. In the end, though, the consensus has come down to the fact that ALH, Allen Hills 84001, was a lifeless Martian rock, and that these were just various artifacts that were found in the rock. Of course, one of the arguments was that this stuff could have been infiltrated into the rock while it was on Earth, so that had to be, unproved, disproved as well. So in the end, we have no evidence today that there is life on Mars. However, we would certainly argue that Mars presently is habitable, and we certainly would argue that the conditions for Mars in the Nochian period, after bombardment for about another 250 million years past that period, that the planet was definitely habitable and something like life could have formed. If it did, it may have been able to adapt to the dramatic climatic change in Mars, and there may be Martian life today in the form of very cold temperature extremophiles and probably subsurface dwellers. So that's our unit on Mars. I hope you have enjoyed it, and don't forget to take the attendance quiz with the magic word that I said, or magic phrase in this case. And then don't forget to watch the videos and then take the lecture quiz itself. And then there's the homework set. So each of those has to be handed in. Now, I'm going to be sending out an announcement that you'll probably have read before you get to this point in the lecture, but I did not realize that Friday, when all of these quizzes and homework sets are due for Module 8 for Mars, was Friday at midnight. So it turns out that that is a school holiday, and the name of that holiday, I think, is called Spring. I don't know what they call it now, but it's on the 10th of February. I know that it used to be called Good Friday before Easter, so now it's a Friday holiday. So what I'm going to say is that I'm going to move the deadline for all of the Module 8 assignments to Monday the 13th at midnight, so that you can have, if you want to take your holiday on the 10th, which is, the university is given to you, and now I'm making sure that I'm, conforming to that so that you have your holiday, and that then you can have your Easter weekend, and then Monday the 13th come back and make sure you get everything for Module 8 handed in by Monday the 13th at midnight. And then don't forget, of course, that on Tuesday the 14th you move into the next module, which is opened on Monday. All right, you guys. You guys have a good one, and I'll see you in the next lecture show. And, if you, as usual, if you need to get a hold of me, don't forget that there's those discussion boards. So far, I've gotten 0 questions on those. And then on Tuesdays and Thursdays at noon, the optional Zoom office hours, I will be sitting on Zoom, and you can just punch into the waiting room, and then I'll let you in. All right, you guys, take care, and hopefully someday you'll be alive and we'll find life on Mars. Bye now.